I'm going to try see how things go this morning. Alright. Unit 2 in your textbook is chapters 5 and 6. The beginning of this, chapter 5, is pretty much review. You don't have to worry too much about, new and totally bizarre things. Chapter 6, get into a few things that are interesting. Alright, so let's see how this works. If this board breaks down and starts giving me trouble, I might just abandon it and start again. Well, when things work consistently, I tend to stick with them. Things kind of work sometimes. All right, so let's start with chapter 5. And like I said, pretty much review. We won't spend too much time on it. We spent a couple weeks on this in honors physics. Today, probably 20 minutes. So maybe a little more than that. So Newton's first law. Okay, just a quick summary of Newton's accomplishments. What's the first law? That's it. The law of inertia. Yeah. Yeah, in the popular realm, they say objects once in motion tend to stay in motion. Objects at rest tend to stay at rest. Okay, until there's a net force acting on an object, they tend to stay in whatever type of motion they're at. Maintain a constant velocity unless a net force acts on them. Can't talk this morning. Who are you laughing at? Yeah, net fork. I'm thinking about dinner again. Okay, so last year we summarized the whole thing. That by saying, all right, if the sum of all the forces on an object equals 0, I'll put a big old if in front, then the thing maintains a constant velocity. Now, mathematically, how can we say that? Acceleration equals 0. That's the whole first law. Took us forever to say it last year. This year, if you add up all the forces on an object, they equal 0, it's not accelerating. Done. Now remember, acceleration includes speeding up, slowing down, but also changing direction. So no type of acceleration at all. Okay. When you talk about inertia, quite often you get into the role of mass. Mass is a measure of an object's inertia. The more mass it has, the more inertia it has. Okay, just try pushing your car out of the intersection when it stalls. Huge amount of mass you're trying to move. And then once you get it moving, once you start pushing it and actually succeed in getting it moving, it's hard to get it to stop. You always have someone behind the wheel ready to step on the brakes. Mass comes into play in the second law. And usually there's lots of little signs all over this room. They're gone right now because my honors physics students aren't at this point. So Newton's second. And you can almost get Newton's first law from the second law. So the second law is extremely important. What is it, sir? You got it. So, mathematically, it's F equals MA. Says, okay, if the sum of the forces on an object are not 0, what does it do now? It behaves in a certain way. And that behavior is called acceleration. And it's probably better, bless you, write it like this. Okay, if the sum of the forces is not zero, then the thing will accelerate, and the amount of acceleration depends on A, the amount of net force, but also B, the amount of mass. The bigger the mass, the more inertia, the less the acceleration. So I kind of like this way of writing F equals ma. I mean, this is the classic, put a heart around it. But this guy here says, all right, here's the cause and effect. The cause is force. The bigger the force, the bigger the top of the fraction, the bigger the acceleration. The bigger the mass, the bigger the bottom of the fraction gets, the less the acceleration. So, I don't know. We always write it F equals ma, but we should probably write it A equals F over m. I got to change all my little signs now. Then I can't say run home to ma. That's right. So, I do like F equals ma traditionally, but yeah. Okay. Oh, then I hit the examples. Wow. That's a lot of lecture. All right, let's do it. Physics examples, 1 of 4. The first one's super easy. If a net horizontal force of 136 newtons is applied to a person who has a mass of 50 kilograms resting on the edge of a swimming pool. I was trying to think of something where it'd be like slippery, give them a push and there's really low friction. What horizontal acceleration is produced? Okay, right now you're thinking to yourself, gosh, Mr. Everly, why don't you give us a hard one? Let's try green. They really don't have white. I gotta see if I can do that someday. Oh, look at that! It's working. Okay, so A equals F over m. Net force, 136 newtons. Pushed on someone on the slippery edge of a swimming pool who has 50 kilograms of mass. And you're like, gosh, that's like before honors physics, right? 2.72. meters per second. Okay. Let's try something harder. That was almost embarrassing. Oh, no. You really do have to hit that button. Okay. A large box of thumbtacks has a weight of 2 times 10 to the third newtons. Oh, well, situations where I have to ask my wife what's in the box, and she said thumbtacks, I think. Being accelerated uniformly over a horizontal surface at a rate of 8 meters per second squared, the opposing force of friction between the box and the surface is 27.4 newtons. How much force is being exerted horizontally on the box? Okay, we're at the point in our lives now. We have to draw a free body diagram. What's a free body diagram? Diagram, you just draw all the forces on it. And the thing about free body diagrams is you only draw the forces on the object. I'm not sure I like the green anymore. Here we go. Only draw the forces on the object, not the forces the object exerts on other things. So there's a little bit of an art form here. So it's got a weight, Fw. Accelerated over, okay, know the acceleration. Acceleration is not a force, so I'll just stick it over here. The opposing force of friction between the box and the surface. So we've got some kind of frictional force. I'm going to call it kinetic friction, FK. We've got our force. When somebody pushes on something, we usually call it the applied force, for lack of a better term. My free body diagram is missing one force. Yeah, the dreaded normal force. So the surface pushes up on the box as well. Otherwise, it would be accelerating downward with an unbalanced force. But sitting on the surface, things don't usually accelerate downward. Okay? So if the forces are unbalanced, run home to mom. Okay? The sum of the forces would be FA minus FK equals MA. We say sum because we're putting in the negative sign for the friction force. It's really FA plus a negative FK. But instead of writing all those signs, we just write it as a subtraction, even though we are technically summing the forces together. And then it becomes pretty simple. But the force required is going to be MA, the force required to accelerate this thing, plus the friction force, because the friction force is opposing us and we have to overcome it. Okay. Just like last year. Nothing too bizarre. So what do we have? 2,000 kilograms of thumbtacks. Oh my gosh. That was a rookie mistake. You guys are paying attention. All right. See if I can get the, or I can just do it right there. You're right. Just divide by 9.8 right in the problem. Okay, here we go. Oh, it still works. All right, I'm going to do that. I just erased it, but I'm going to say 2,000 newtons divided by 9.80 meters per second squared. Turn that into a mass. Acceleration, 8 meters per second squared. Frictional force, 27.4 newtons. Not too much frictional force, given all that weight. I'm just about out of room. What you got, sir? 1660, he says. All right. 1,660 newtons. If you take my picture seriously, to the right, opposing the friction force. Okay? And that's a great point. Make sure you got mass there, not weight. Rookie mistake. All right. Very good. Turned off all the dings. It used to ding every time you hit a button. Like, bing! Drive you totally nuts. Okay. I might need more room for this one. I don't know. I'm recording this for my second hour class because you have the senior class meeting today. And they're going to be like an hour behind. So I toyed with the idea, since this is not terribly difficult, of just making a video. And that way they can watch the video and kind of catch up. Problem with that plan is I'll probably hear from Em or Tabitha about this. Stop caring? How could I stop caring? Well, you know, sometimes the complaining is kind of entertaining. Hi, Emma. Yep. Abby Worson too. She's sitting next to Emma, so they kind of they're kind of helping each other out. Yeah, they kind of bounce off each other. It's pretty good. Okay. Now it gets more complicated because we go 2D here. Not everything's on the X and Y axis. So three forces act on a 138 kilogram box of chicken nuggets, as seen from above. Find the acceleration of the box in unit vector notation as it slides across the frictionless floor of a fast food establishment. F1 is a force of 150 newtons at 45 degrees. F2 is a force of 100, where did that come from? 83 newtons at 0 degrees. And F3 is a force of 235 newtons at negative 28 degrees. Oh my gosh. We need to find the acceleration of this thing in unit vector notation. Why in unit vector notation? Because I'm a nice guy. Alright. So, I'm going to choose some colors here. Obviously, first task is to do what? Break them down. Alright, so F1. Ah! See, I love this thing. It just fills my heart with joy. There we go. Try that again. Okay, so we know this angle right here. This is that first angle of 45 degrees. So I'll write it over here. Write down my givens. 150 newtons. Theta is 45 degrees. So we've got F1 sine of theta, F1 cosine theta. Okay, let's try some blue here. Come on. Oh, look at that. Love it when technology works. Use the Greek letter alpha for him. We'll say F2. I beg your pardon, F3. F3 is a force of 235. Yeah, I think that was Jackie. You okay, Jackie? All right. It's coming from the back row somewhere. Okay, so the point here is that if you're going to find the acceleration, it's going to be the sum of the forces over the mass. So our job here is going to be find the sum of the forces on the x-axis and divide by the mass. And I'll have the acceleration in the x direction. Find the sum of the forces in the y direction, divide by the mass, and I'll have the acceleration in the y. So this is not so terrible. There he is. And he is participating. All right, so let's tackle this. It's not hard, it's just a lot to do. So on the x-axis, we've got F1 cosine theta. We have F2, and we have F3 cosine of alpha. I'm using the positive 28, by the way, so I'm letting, I had theta there. That was, I'm surprised someone didn't yell. Slight error on the writing down my givens. There we go. So F3 cosine of alpha, make sure you put in a positive 28 there. We're just using the trig to break this down. Don't get too deep into what the heck is going on mathematically here. It's just simple trig. Okay, there's my I hat, my J hat, and I better label these guys. I've got F3 cosine of alpha and F3 sine of alpha in the negative direction. So I'm kind of running out of room here, but this is going to be F1 sine theta minus F3 sine alpha divided by the mass j hat. Whoa. Hope people can see that on the video. Good golly, Miss Molly. Alternatively, we could just calculate the force in unit vector notation. Once you have that, divide both components by the mass. But that's going to be our solution without numbers. So, do the calculation real quick. We've got, what? 150 cosine of 45 plus F2, which is 83 newtons, plus 235 cosine of 28 degrees, all over 138 kilogram box. And this will be our acceleration in the x direction. That's a little prettier. Acceleration in the y, F1, 150 sine of 45 degrees, minus 235 sine of 28 degrees. That's right. Divide the whole thing by 138. And we'll get our two accelerations, one for the x and one for the y. Okay? I bet Mitch has those all punched out by now. You bet. 0.03 was last number, sir? 0.03 j hat. Oh, just 0.03? Yeah. Okay. It's 0.03086. Well, that's only one sig fig there, Doc. Oh, you're right. All right. 0.03. Ooh. Okay. So, do we get two sig figs? So we can put a 1 there. How about 0.031 j hat? So, and is the x1 okay with 3 sig figs? And we do have 2 on the 45, so we might round that one up to 2.9. How's that? So for our official answer, we'll say 2.9 I hat minus 0.031 j hat meters per second squared. Okay? So nothing too terribly difficult for so early in the morning. F equals ma is the same as it was last year. I have one more example. Then I can pause my yammering for a little while. Oh, and I capped my marker. That's not a good thing to do when you're in the middle of something. There we go. Has to shake hands with the computer again. Oh yeah, this one's pretty good. Okay, a small space probe with a mass of 400 kilograms is propelled by a force of 4,700 newtons at 0 degrees, provided by its thrusters. So it's got little gas-powered thrusters on it. It's got a pretty good sized force, 4,700 newtons. The probe, however, experiences an acceleration of 5 meters per second. Oh, 5 meters per second squared, 35 degrees. Typo. What is the magnitude direction of the second force on the probe? Now this actually has some basis in reality. I don't know what the status of it is right now, but one of the space probes, one of the Voyager probes that was launched in the 70s, when it reached the edge of the solar system, had a mysterious force on it that they couldn't explain. So, tractor beam by aliens, Twilight Zone, something mysteriously, the gravitational pull of some mysterious dark object we haven't discovered, who knows. But it's kind of a cool mystery. We knew exactly what the acceleration of the probe should be, but the actual acceleration was a little different. Must have been a second force. So that's the inspiration for this problem. Is okay. what's the magnitude and direction of that second force? Okay? You want to give this one a shot on your own? Shall we do it together? How you feeling? Try it on your own? Okay. All right. Here's our space probe. Oh, look, it's actually right. And we have one force on it that we know. So when we know something, we write it down. We got a force in the positive x direction, and it is a force of, I'll put my givens up here so I save some room. 4,700 newtons, 0 degrees. And then we've got a mysterious acceleration, though, that goes off at an angle. Now, that mysterious acceleration means that the net force is in that direction. Okay, so we've got, the sum of all forces pointing that way. Because according to F equals ma, not only does F equals ma, but the acceleration is in the direction of the net force. So we've got this weird situation where this green F1 is pointing to the right, but the acceleration is off at some angle, 28 degrees. Now, we could say then the sum of all the forces is going to be the mass times the acceleration, or 400 kilograms. Yep, 3 sig figs. Times the acceleration of 5 meters per second squared. We get the magnitude. Uh-oh, I went right off the board. There we go. So the net force is like 2,000 newtons at an angle of 35 degrees. Okay, switch to a better color here. So what I'm thinking is F1 plus this F2 that we're looking for must add up to the sum of the forces. So what if we did this? What if we said the sum of the forces minus F1 equals F2?
Shay Cole, Ingrid Grable, Curtis Lynn, Taylor Mize, Ryan Mize, Logan Mulholland, Connor Burns, Peyton Stallings, Judy Tim's office.
Quite a list. So, is my equation making sense? I'm going to take all the forces, the sum of the forces, subtract the one force we know, and what should be left is the force we're looking for. You're all looking at me like I'm nuts.
Any students who want to be in the spirit camp, please come down to the first floor office.
You want to be in spirit camp? Okay, good.
In front of the first floor office.
Alright, so how is the 2,000 oh, that's the result.
Exactly. So there's some other force that I haven't drawn yet that's pointing in some direction. And this force plus the mystery force equals the red force. So I'm saying, okay, this guy we know. We know it's 2,000. Come on, please. All right, 2,000 times the cosine of 35 degrees plus 2,000 times the. I actually put the times. That was really weird. Times the sine of 35 degrees. Oh, and this is I hat and J hat. Put in our little symbol. Then F1 is just 4,700 newtons, 0 degrees. So I'm going to say that's 4,700 newtons I hat plus 0 J hat. And I'm going to subtract this guy from the net force, and then I'll have F2. Am I making logical sense here? Sir?
So whenever the acceleration is going something that's always greater than that force, that's never going to be its own force.
Bing, 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 you win. That's it. Whatever direction he's accelerating, that's the direction of the net force. So if you have multiple forces on an object and it's accelerating to the north, you know the net force is to the north. Beautiful. All right. So we do the subtraction, and I get negative 3062 in the I-hat direction. We get 1147 in the J-hat direction. And it's all in newtons. In fact, all this stuff is in newtons. So mystery force, I can't talk. Mystery force is pointing to the left and up. I guess that kind of makes sense. So it's kind of doing one of these. Okay, and we like to know the magnitude and direction of that force. And I just drew the quick and dirty diagram if you hadn't noticed. So I've got 3,000. Can you even read this? No. There's only one color that works on black, and that's green. Oh well. 3,062 that way, 1147 that way. So F2, magnitude, square root of 3062, squared plus 1147. Okay, now it's just details. Coming up with the magnitude and direction. So, squared plus 3062, squared, take the square root, we get, wow, that's what I'm getting, 3,270. Okay. Angle. Gosh, what shall we find? I think I'm going to find this angle right here. Probably want to give it a different name, right? Call it alpha. And we'll say, okay, alpha is the inverse tangent of opposite over adjacent, so I need the 1147 on top. That's the only reason I draw the diagram, so I can visually see what I need to put on top. I hate memorizing things. Figure it out. Inverse tan, 1147, divided by 3062. Answer, it's about 20 degrees. 20.5 degrees. Now in space, there's really no north, south, east, or west. So if I said 20.5 degrees north of west, people would kind of laugh at me. So I think what I'm going to do is say, what if we say it's like 159 degrees from the x-axis or something? Okay, it's like 159 degrees from the positive x-axis. So, we win. 3,270 newtons, 159 degrees from the direction of the original force, the thruster force. Okay, pretty hefty force. So that could be an alien tractor beam rather than a distant gravitationally massive object. Okay, so the theme of this chapter is not so much new stuff, but last year's stuff a little deeper. You know, there's some problems you have to cogitate over in order to make them work, but the concepts are the same. The physics is not terrible. Okay, how you doing out there?